So for today, we're going to start with systems of equations. Now, these are systems of linear equations here. Ned, you can pass those back. Ned's going to pass back your problem sets. Please don't get too distracted yet. The solutions are on Moodle, so you can look at your grades right now, and you have group members, so feel free to share them with each other. Okay? Take a minute or so to look at those before we get started. Again, take a minute or so to look at those before we begin this. You do not need to write all of this down, guys. You can read through what's on the board right now. You don't have to write every bit of it down. Again, a lot of you guys improved, and I was very happy to see that. You're getting the hang of it, so hopefully it'll get even better. I want to see everything in 90s or above with these notes. I really do. Just because you have a limited amount of resources to do these. Some people are struggling a little bit still. Hey, please work on these a little tougher next time. The solution is on Moodle. It looks like this. I typed up the solution for this one. Okay, it's not handwritten. So feel free to take a look and see how it looks to you. Compare it with your answers. If you have further questions that aren't answered, please come see me. But make sure you look at the solution first so you can try and solve these problems on your own. I want you to be able to do that and take a look at them. Don't just assume that you're going to have long and know what it means. All right, so section 3.5 says, first of all, does anyone want to read for us? Nice and loud and clearly, Summer?
A set of two linear equations with the same two variables is called a system of linear equations. Any ordered pair that satisfies both equations is the solution to the system. Also remember that a solution to a linear equation is a point on the line. Therefore, if the ordered pair is the solution to both equations, then it is a point that is on both lines. If you were to graph two linear equations on the same coordinate plane, what are the possible ways they can or cannot intersect?
Okay, so now we're looking at where we have two linear functions, either crossing or doing something on the plane. We know that in the past we've said a solution is a point on the line. Well, if it's a solution to both equations, then it's going to be a point on both lines. On both lines. Now, what are the possible solutions if we're graphing two lines together? Good. Intersecting is the one way to start. Very good, man. So the first thing we're going to look at are lines that intersect somewhere on our graph. And if I can use the smartboard, there it is. There's our intersection. Okay, there's our intersection, which is also called our solution. Okay? What's another option? What else can the lines do? Besides intersecting lines. Like parallel lines. Very good. Two lines that are parallel. And Michael, when two lines are parallel, do they intersect? So is there a solution to this? Because they don't intersect, right? Again, a minute ago we said the intersection is the solution. So if these don't intersect, then they don't have a solution. Third, there is one other option here. And this one's a little bit tricky to remember. Linear functions. Yes, parabolas can intersect differently. Perpendicular, though, they're still intersecting. You're right. Perpendicular is a specific type of intersection, but they're still intersecting. This one is one that people don't realize all the time, because it's not obvious at all. I'll give you an example, okay? If I have a function or a linear function that says this, 2x plus 3y equals 6, and I also have 6x plus 9y equals 18. 6x plus 9y equals 18. Yeah, good. Say it. They're identical. Just multiply everything by 3. Triple the first term. Triple the second term. Triple the constant term. Aren't they identical? So really, if I divide the second equation by 3, don't I get back to the first equation? So since these two functions are the same, what are they going to look like? Yeah, it's going to look like one line. Now, specifically, I'm not going to use this example anymore, but specifically, here's what it'll look like. Here's the first linear function. Here's the second linear function. The lines are the same. So, somebody tell me, where do they intersect? shared. This point is shared. This point is shared. So is this one. So is this one, and so forth and so on. Therefore, there are an infinite amount of solutions. Because there are an infinite amount of intersecting points on these two lines. On these two lines. Is that clear so far? So to summarize, so you can see, I summarized that on the next page. So that's what we're going to go through. So, intersecting lines have exactly one solution, and we call this consistent. Consistent. This last term, to be honest though, just to give you guys a little outline, and then you're probably not even familiar with these bottom terms, because they're not really used. Okay? So these terms at the bottom here, this term here, not really as important as the first ones, okay? They're old school terms that your book uses, so you want you to be familiar with them. But you're not going to see them all. Now, intersecting one solution. The same lines, and we reversed the order when we discussed these, so just be careful. When they're the same line, we did parallel first. When they're the same line, we call them coinciding, and that is a good term to know. When two things coincide, they are on top of one another, or they're the same thing. They coincide with one another. They overlap. When two sets coincide, there's some overlap in their solution. And there are infinite amount of solutions. And then the second example that Michael gave us was the parallel lines, where there are no solutions. No solutions. So we have three possible scenarios that we're going to look at today. Three possible scenarios. Questions? Are we good on this so far? All right. Let's take a look at some examples. The first one. Solve the following system of equations algebraically. Well, if I say algebraically, what's another way to solve these? Based on what we just looked at a minute ago. Graphically. So, you can always check your solution graphically, or if it's an SAT example, solve it graphically, that's fine. Go to your calculator, plot both of the graphs, use the function called the intersection function, which we'll take a look at in a minute. But I want to solve this algebraically first. Now, some people might remember, there are two methods to solve systems. There are two methods that you've learned so far. I'll teach you guys a third method by the end of today or maybe tomorrow, depending on how fun we get. Anybody remember the names of one of those two methods? Substitution is one of them, and elimination. Two methods. Tell me, there is a third we're going to go over later today. Yes. We're talking about, hold on for a second. For the two methods here, substitution and elimination, can anybody tell me what would be better for this example? Alejandro? Can you tell me why now? They give you one of the variables solved for explicitly. Take a look at that first equation. You see how it's solved for y there? When it's solved for one of the variables, automatically go to substitution. Is that clear? And you want to write this down as your note. When it's solved for one of the variables, as it is here in the first equation, automatically think about substitution. Because you can simply substitute the expression. So take 2x plus 4 and substitute it in the second equation for the variable y. Because that's what the definition of y is. Again, it's like a synonym in English. If you have a synonym in the same words, you can substitute it in its place. Right? Instead of saying large, you could say enormous, or you could say grand. Okay, those are words that mean large. You can substitute them in. Same thing here. So take the 2x plus 4 and plug it in the place of y. Okay? Again, this here is really y. So we've substituted in. And now what happened? How many variables do I have now? Just one. It shows up twice, but it's only one variable, and we solve. Let's solve this for x. Distributing the -2. We all agree with that? Again, the -2 needs to be distributed. Then what do I have to do? Good. negative 3 there, guys? It's not showing up. Negative x equals negative 3, yielding x equals 3. Now, first of all, do we all agree with x equals 3? Want to get the same answer? What do I do to get 1? Erickson? Yeah, plug in x. Where, Erickson? Good. Into one of the originals. Now, you answered correctly. Into one of the 2 originals. Erickson, why did you choose the first one to plug into?
Because we already isolated y.
Yeah, y is isolated, and we're looking for y, aren't we? So you're absolutely right. Plug it in. What do you get, Nick? 10. 3 times 2 is 6. 6 plus 4 is 10. So I'm just going to put an arrow and put y equals 10, showing me that after plugging in, I get a 10. So as an order of pair, I write my solution, 3, 10. Any questions on this? I know it's a little bit of review, but we're going to do some that are tougher than what we've done in the past. Okay? Today's more of let's recover and think about what we've done here. We're going to talk more about that other math in a little bit. Now I want to go into this graphic to prove that we're correct. Take out your calculators, please. Please go to y1 and type in our equation 2x plus 4. Now, in y2, we're going to have to solve for the second equation for y. We're going to have to solve the second equation for y. So let's go ahead and solve the second equation for y. I'm going to move the y over as a positive, making this 3x plus 11 equals 2y. Okay, again, 3x plus 11, which is not very clear. Okay, again, move the 11 over as a positive, move the 2y over as a positive, divide by 2, giving us y equals 3x plus 11 all over 2. Okay, that's going to be our equation. 3x plus 11 all over 2. Oops, what should I put around the 3x plus 11, everybody? Erickson? Parentheses. Sorry, I said everybody. That's one person. 3x plus... Doesn't work. Plus 11 over 2. Now, when I graph these, if I forget what my axis looks like and I want to see a 10 by 10 grid, remember to press zoom and then zoom standard, which is number 6. So just press the number 6 key. It'll make the grid automatically negative 10 to 10. Well, it looks like at first they don't intersect, right? Can't really find it. But it looks to me that it might intersect if I keep following this graph up here, right? All the way up there. So what should I do to my window settings?
Go to zoom.
I can zoom out, that's one way to do it, but there's an easier way. I don't really like the zoom function because it chooses its own arbitrary numbers. Could you give me another way? Summer?
Can you just use the arrows and follow it all the way?
You could use the arrows, but it's going to go off the grid. Let's go to our window, please. Everybody press window. Oops, window. Now, under window, I want to go higher on the graph, don't I? So I want to change my y max. It's right now going from negative 10 to 10. Make the y max 20 instead, please. And then press graph. Using the window function is much more useful than using the zoom out and zoom in, because you might know where you want to go. Now, I want to find the intersection, and it's not very clear. Would you all agree with me? Now, I can use the trace key and try to estimate it, but that's not a really good technique, estimating, right? We want an exact value. Anybody tell me how I can get this intersection here? Is it new to us to use this? Okay, let's step through it then. So there's a function on here. See this word calc? It just means calculate. Remember this whenever you're trying to calculate an answer. So press second, and then press this trace key, which will bring up the calculate function. Take a look at number 5. What does it say? Intersect. So let's choose number 5 now. Now, you see a flashing tick mark, right? in the middle of the screen there. I want to bring it near the intersection. So press to the right, please, until it gets somewhere close to the intersection, which is approximately over there, right? So let's hit enter. Then it's going to say on the second curve. So now, the first time I was on the first line, now I'm on the second line, but because it's so close, I can just hit enter again. So hit enter again for the second curve. Then it asks me, do you want to give a guess? And you might want to give a guess only when there's like 4 or 5 intersections, and you have to guess at the nearest one. But for the sake of this class, when there are linear functions, there's only one intersection. So hit enter one more time. And take a look. What does it read out as an answer? 3, 10. Exactly our solution we got, 3, 10. Again, to step you through this process, you plot both functions, you graph them, open your graph up by using the window settings so that the intersection is showing up somewhere, then press second calculate. When you press second calculate, number 5 is the intersect function. You then choose a spot along the first graph, or the first line, that's near the intersection. Choose a spot along the second line. Then you press enter on the guess function, and it gives you the solution. Questions on this? Very good way to do this on an SAT problem. If you're given both functions and you want to just get the solution, just plot them together and find the solution. Okay? Pardon me.
If you bring up a table, just look.
You could bring up a table, but what happens if the answer is a decimal? Right? So the table does work if the answers are integer values, and you have to sit there and try it, right? But for the most part, I would use the intersection function. Okay? Very good question. Very good. Let's go to our next example. And just to show you, on my graph, you'll see it is also 310. Okay? And I put this on your notes so you can see. Let's go to number 2. Let's go to number 2. Solve the following system of equations algebraically. Algebraically. So we're not solving by graphing here, we're solving algebraically. For this problem, can somebody give me a starting point? A starting point. A method that might be easy to use here. And a reason for your answer as well. And a reason for your answer. Got a minute? Yeah? Oh, sorry. Sorry?
For both the equations, you can isolate the y value.
You could isolate the y value, sure. Definitely works, but there's an easier way. Okay, Erickson?
Isolate X.
I'm sorry?
Isolate.
Isolate x works also, but there's also an easier way. Alejandro?
Multiply times negative
Which one?
the x plus y.
Good. So what method would you choose? What would that be? Elimination. Let's go through this. Do you see how they're lined up, everybody? See how everything is lined up? Here's like your x column, here's your y column, here's your constant column. When they're lined up like that, especially when there's a 1 coefficient somewhere. See this x term in the front of the second equation? Its coefficient is a 1. Whenever there's a coefficient of a 1, there's a good chance it's very easy to use elimination method. So let's go ahead and do that. Now, please follow what I'm about to say, and I guarantee you this might be new to some of you, what I'm going to show you. Label your equations as 1 and 2. So here's what I want you to do. On the side of this equation, label this as 1, label this as equation 2. And I'm putting parentheses, and I'm putting a good space there. This is not negative 7 times 2 or 1 times 1. I am not multiplying by 1 and 2. 1 and 2, those two values are the names of the equations. This method will help you organize your techniques. Now, Alejandro, repeat to us again what you said you would do here. Very good. I like the way you said that. Multiply equation 2 by negative 3. So what I'm going to write is this. Okay? I'm going to write equation 2 times negative 3. And then, Alejandro, what am I going to do with those equations once I do that? Yeah, I'm going to add them together. Because it's going to give me a negative 3 here in front of this x. And when I add them, the x's will eliminate. Hence the name, elimination method. So I'm going to add this to equation 1. That's what I call my command. In computer coding or computer engineering, have what are called commands. This is your command. You're taking the second equation, you're multiplying by a constant of -3, and you're adding it to the first equation. So I'm going to write that out now. So what do I get when I multiply this entire equation by -3? Tell me what I get, Summer.
Negative 3x minus 55 equals positive 29.
Very good. And equation 1 remains the same, right? We have not altered it. So just write equation 1 down now. Oh, that's -3x. Let me rewrite this. It's negative, I apologize, -3x. There's a negative in front of that 3. It's killing me. -3x. All right. Now, I rewrite the other equation as 3x plus the 4y that was there equaling +1. Put a line below these equations and simply sum them together. Summing them together. The -3x and 3x, what happens? Everybody. They cancel, right? These cancel each other out. How many y's am I left with? -11 of them. Very good. 21 and 1 gives me 22. That's all right. That's y equals. Again, the whole method here is to eliminate the variable. That's why it's called elimination. We can eliminate them, yielding only one variable and one equation, and then sum.
What would happen if you did 3x plus 4y equals 1 and over the negative 3x?
If you flip the order,
Like if you did,
The way it was right now, not the way you
if you
stated
did
it.
equation 1
plus
plus
-3 times equation 2,
yeah.
you tell me what happened. What? Addition is,
Oh,
there it is. Addition is commutative. Doesn't matter if I put these equations in separate spots. Why did I multiply by -3? Sorry?
It would be easier than multiplying equation 1 by 5 and by -5 and say equation 2 by -4.
Yeah, see here, there's a +3. To get rid of a +3, I want this to be a -3. Right? That's the only way they'll cancel. Now, what Summer was saying was this. If you multiply this by 5, this becomes 20, right? You can multiply this by -4, this will become -20, and then you can cancel the y values. But it's easier just to multiply one of the equations, right? Instead of both. That's why. So our goal, I want to write this down, our goal is to get coefficients that are opposites. The goal is to get coefficients that are opposites, so they can cancel each other. Okay? Again, whenever you're doing elimination method, it's different from substitution. You want coefficients that are opposites so that they can cancel one another, like they did here in this problem. Whereas with substitution, we want to isolate a variable and then substitute in. So we want to get x. If I want to get x now, what do I have to do with the y value I got for my solution? Karina?
Like 1 or 1 of the equations.
Yeah, plug it into one of the equations. Which one might be easier here, Karina? The second one. How come? Yeah, take a look at x, everybody. X is by itself. And if we're trying to figure out what x is, plug in the -2 right here in for that y value, giving us x plus -10 equals -7. Okay, plug it in the second equation because the x value has a 1 coefficient. It makes it easier. Nick, what do we get?
May I go use that?
Yes, you can. Tell me what do we get first.
Negative 17.
Be careful. It's -10.
3.
Thank you. Okay, x equals 3. X equals 3. As an order of pair, I write it as 3, comma, -2. Any questions on this problem? Now, how can I check this? As we did last equation? Or last example? What did we do last time to check?
So just like graph.
Yeah, we graphed it, exactly. Check by graphing. What's another way to check it though, guys?
Just put it into the equation.
Yeah, take original equations. Now, you are all smart enough and old enough to just check on your calculator. So you can do that as well. It's up to you to decide. But if you check on your calculator, you need to make a statement that says, if the problem says, solve the equation and check your answer, you should write, checking graphically the solution is 3 to -2. Okay? And if your answer is wrong, and you say checking graphically, the solution is this, I'm going to probably assume that you might not have checked. Because if you check on the graph and you get a different answer, that means you might need to go back and look at this. Personally, I would check this by hand. Because I don't want to solve for y twice and then have to graph it. You all agree with me there? You have to solve the first one for y, solve the second one for y, and then graph them both. I don't want to do all that work, so I would check this by hand. Okay? Let's take a look at this nice example before the bell's going to ring. What we're going to do is we're going to finish this tomorrow because we're not going to get through all the examples. I'll tell you that right now. Okay? We won't get through all the examples yet. So we will finish this one tomorrow. So I want to take a look at these quickly. So let's try and get the first letter, I. Solve the following systems. Method, please. Method for letter I. Summer.
Maybe once you solve the second one once you put the x on the other side of the equation for the second equation in one, you could probably use substitution.
Okay, your method is right, substitution, but your statement might be a little off.
Elimination. Can't you just sum together like opposite?
You could use elimination, but Summer, you said substitution. I like that better here.
Yeah.
Can somebody tell us why I like substitution better?
Because y is very isolated.
Y is isolated here, isn't it?
Yeah.
So go like this. X plus 2. And take this quantity that's solved for y and plug it in right up here for that y value. Okay? So let's do that. We're going to have -1/2 x plus 4. And now just solve by distributing, right? So let's do this. X plus, what's 2 times 1/2? What happens with 2 and the 1/2 when we multiply them? Yeah, we just get a 1, but it's a -1/2. Very good. So this is going to become -x. This is going to become 8 equals 1. Finish this up and see what happens. You're going to notice something. Tonight, no homework, guys. Okay? Take the night off. Catch up on the work. Tomorrow we'll finish 3 and 5.